Hello everyone, I'm Shen Gao. I come from Beijing Institute of Technology. I'm going to talk about our work on colorful edge star decomposition. This is a joint work with Professor Ronghua Li, Hong Chaoqun, Hong Zhicheng, Professor Ye Yuan, and Professor Guoren Wang. This is the content of this talk. First, I'll introduce the background of this work. Then, I'll discuss a new cohesive subgraph model called Colorful Edge Star model. Finally, I'll show our experimental results. Graph model has been widely used to represent the relationship among entities in a wide spectrum of applications, such as social network, internet, road network, and Internet of Things network. As a result, we are nowadays facing a tremendous amount of large real-world graphs. Real-world graphs, such as blog network, Twitter social networks, and biological networks, often consist of cohesive subgraph structures. Mining cohesive subgraph from a graph is a fundamental problem in network analysis, which has attracted much attention in the database and data mining communities. There exist many different cohesive subgraph models, including K-core, K-trust, and H-click K-core. These models have different cohesiveness measures. Mining cohesive subgraphs based on these models leads to the resulting graph with different properties, and also often requires different levels of computational effort. Here we compare existing cohesive subgraph models. The widely studied K-core model can be computed in linear time, which is really fast in graph analysis tasks. But this model can't identify denser regions of a graph because it only considers degrees of the nodes. The H-click K-core and H-click density subgraph model are higher-order variants of the traditional K-core model and the density subgraph model. Recently, these models have attracted much attention in database and data mining communities because they can be applied to higher-order graph analysis tasks. However, the computation of those models is often really costly on large graphs for relatively large H values. This is because all those H-click-based higher-order cohesive subgraph models need to count the number of H-clicks, which is often costly for large H values. To address this issue, we first propose a novel higher-order cohesive subgraph model based on a concept of colorful H star. Our new model can be considered as a relaxation of H-click core model and can also be applied to higher-order graph analysis. Second, we propose a DP algorithm to compute and a novel updating technique to update the number of colorful edge stars for each node. Equipped with these two algorithms, our model can be computed in near linear time. We also present a colorful edge star core-based graph reduction technique to solve H-click density subgraph problem. We conduct extensive experiments on 11 large real-life datasets to evaluate our algorithms. The results demonstrate the efficiency, scalability, and effectiveness of the proposed algorithms. Graph coloring is a procedure that assigns an integer color value to each node, so that no two adjacent nodes have the same color value. An H-star is a tree with one central node connecting to the other H-1 nodes. We call an H-star colorful if nodes in this H-star have different colors. Here are examples of a colorful 4-star and a colorful 5-star. Note that after performing a graph coloring algorithms to a graph, nodes within an H-click have different colors. Therefore, any H-star in an H-click must be colorful. This provides us an intuition that if we pick a colorful H-star from the graph G, this colorful H-star is more likely to be an H-click. That is, a colorful edge star can be considered as a relaxed definition of edge clique. Here we can see that the subgraph induced by this colorful 4 star is actually a 4 clique. To formally define our colorful edge star core, we first propose the concept of colorful edge star degree. Given a node U, the colorful edge star degree of U is the number of colorful edge stars centering on U. For example, the colorful 3-star degree of V5 is 13 because there are 13 colorful edge stars centering on V5, which are enumerated here. We define colorful edge star K core as the maximum subgraph, in which the colorful edge star degree of each node is at least K. We present various colorful edge star cores and edge clique cores of this toy graph. In this example, we can clearly see that these two kinds of cores are the same, which means that the colorful edge star core is a good approximation of edge clique core. Therefore, our model can also be used in higher-order graph analysis applications. For the edge clique densest subgraph problem, the edge clique K-max core has been proved to be a edge approximation solution. Therefore, our colorful edge star core can also provide a good approximation. Now, one of the questions is how to compute colorful edge star core decomposition. Basically, we can use the peeling-style algorithm to solve this problem. That is, removing the node with a minimum colorful edge star degree. But how to compute the colorful edge star degree of each node and how to update the label's colorful edge star degrees after removing a node? Below, we'll introduce our DP algorithm and updating algorithms to address these issues. As we know, computing colorful edge star degree is equivalent to compute the number of ways to choose H-1 labels with different colors. Here we propose a dynamic programming algorithm to compute this number. Given a node U, we first divide the labels of U into different groups according to their colors. Then, we define dpij as the number of ways to choose j labels with different colors from the first I groups. Note that dpij can be divided into two cases by considering whether or not select the node from the ith color group. Then, we have this recursive DP equation. From this equation, we can say that the time complexity of DP algorithms is this, because J has been bounded by the degree of U. A running example is shown here. The colorful edge star degree of V5 can be computed by using the DP algorithm. Here we consider the problem of updating the colorful edge star degree of a node U when one of its label node V is deleted. To this end, a straightforward algorithm is to recompute the colorful edge star degree of U after removing V by using DP algorithm. Clearly, such an algorithm is inefficient when we need to frequently handle edge removals. A natural question is that can we have a better algorithm to update the colorful edge star degree of a node without recomputing from scratch? We developed a novel algorithm to achieve this goal, based on our observation that the removal of V reduces color counts. Thus, it only affects the results computed in case 1. Therefore, it's unnecessary to recalculate the entire DP table again because the result in case 2 remains the same. Therefore, our idea is to decompose the DP equation into 2 different cases. Specifically, let's consider a node U and a color value. The node U has 2 types of colorful edge stars, with or without a node having the given color. Let Gi and Fi denote the number of the former type and the later type respectively. Therefore, after removing a node, only GI needs to be updated. The proposed updating technique consists of 3 steps: restoring, updating, and regenerating. In the restoring step, our algorithm restores Fi and GI on the basis of DPI. In the second step, the updating algorithm updates the color group of these labels. In the last step, our algorithms calculate GI and DPI based on Fi and the updated color group of these labels. A striking feature of this updating algorithm is that it can achieve a very low time complexity, that is OH, for an update. This feature can help us compute the colorful edge star code decomposition in linear time. We collect 11 large real-world graphs. These datasets cover various domains, such as online social networks, collaboration networks, internet topology graphs, scientific computing networks. The detailed statistics of these datasets are summarized in this table. We first show the results of the colorful edge star code decomposition. In this experiment, we compare the running time between algorithms with and without the updating technique, and the algorithm using binary search to compute the colorful edge star K-max score. We can say that H star CD is 2 to 7 times faster than H star DP over all datasets. These results confirm our theoretical analysis in our paper. Note that the performance of the binary search algorithm is comparable with that of updating algorithm, and sometimes even slightly worse. This is the binary search method has an additional log factor, although it doesn't need to compute all the core numbers. Here we evaluate the scalability of our algorithm on 8 different datasets. These datasets can be divided into 2 sets according to their numbers of edges, for medium-sized graphs and for massive graphs. As can be seen, the running time of our algorithm increases smoothly as the graph size increases on both medium-sized and massive graphs. Moreover, all the curves are nearly linear, indicating that our algorithm scales very well in practice. These results also confirm the near-linear time complexity of our algorithm. We evaluate the memory usage of our algorithm on various datasets, for H is equal to 4 and 6 respectively. We can say that the memory cost of our algorithm is insensitive with regard to H values on all datasets. This is because the space complexity is dominated by OM. For the graphs with a relatively small color number, the space usage is slightly larger than the graph size. These results confirm the near-linear space complexity of the updating algorithm in our paper. For the edge-click densest subgraph problem, we implement 2 algorithms. First, H star PP, a graph reduction technique based on the colorful H star model. This is an approximation algorithm with theoretical guarantee. Second, H star MMPP, a heuristic approach using the colorful H star K-max score as an approximation solution. We compare our algorithms with 3 state-of-the-art approximation algorithms. We plot the running time achieved by each algorithm as a function of H varying from 3 to 9 on various datasets. As expected, the running time of 5 approximation algorithms increases as H increases. We can clearly say that both the colorful H star core-based algorithm and the heuristics approach are significantly faster than the other competitors, and the exact algorithms take the most time on almost all datasets. We use a relative error as a metric to evaluate the approximation performance of different algorithms. These results indicate that The state-of-the-art algorithm is very accurate on most datasets, but it is intractable on large graphs for large h-values. And the colorful H-star core-based algorithms produce high-quality results using much less time. This table shows the statistics of the original graph, the reduced graph, and the H-click K-max code. In this table, delta is a part of the removed nodes. This number, along with density and click density, can be used to measure the effectiveness of pooling rule. From this table, we can say that our pooling strategy is very effective. It can largely prune the nodes that are definitely not contained in the H-click K-max code. These results also indicate that our colorful H-star core model can also provide a very good approximation for the H-click density subgraph. Here we study how graph colorings impact the performance of the colorful H-star core decomposition and qualities of the colorful H-star maximum core. We compare 4 popular graph colorings, which are coloring the nodes following a non-increasing order of degree, and following an inverse degeneracy ordering, and in the order they appear in the input graph representation, and coloring an uncolored node whose colored label nodes use the largest number of distinct colors. The left figure shows the node distribution of various colorful H-star K cores for H is equal to 3 and 6 when using different coloring algorithms. Note that both x-axis and y-axis are in log scale. Thus, the distribution of colorful H-star core numbers generally follows a power law distribution. The node distributions are very similar in the setting of 4 different coloring algorithms. A slight difference is that nodes in the third figure, FF, are more scattered. A possible reason is that the FF heuristics uses the larger number of colors to color nodes. The right figure shows node distribution of different H-click cores. Again, the distribution of H-click core follows a power law distribution. In addition, we can also observe that 3-click cores and the colorful 3-star cores have the similar node distribution. Besides, these 2 kinds of distribution share the same trend when H values get larger. Therefore, our colorful H-star core model can still be seen as a good approximation of H-click core. We evaluate the performance of our heuristic algorithm H-star MPP in terms of time consumption and relative errors. The detailed statistics are shown in the left table. As can be seen, the SD heuristic consumes more time than the other 3 coloring techniques. This is because the other 3 colorings color nodes following a fixed order, but SD selects an uncolored node dynamically based on the number of distinct colors of their labels, which can be very costly, though it produces slightly higher quality colorings. We can say that FF has a larger relative errors. The results suggest that the estimating precision seems to match the number of colors used in graded coloring algorithms. And the reason might be that when less colors are used in coloring algorithms, a colorful H-star has a high probability to be an H-click. Thus, it can be a good approximation of a click. Overall, the degree coloring is the best method in terms of both runtime and approximation quality. This is why we use degree as a default coloring technique in the proposed solutions. That's all. Thanks for your attention.